All right, question number 9. We have a rectangular coil rotating in this direction. It says, state the minimum angle in degrees to which the coil must rotate for the EMF to reach its maximum value. Now you remember that the flux going through the coil will be maximum when it's in that position and minimum when it's in that position. So if you think about the flux, it's going to do something like this. But the EMF is maximum when the rate of change of flux is at a maximum. So if we were to overlay this is where it's maximum rate of change. That's where it's going to be a minimum when there's a minus sign there. There the gradient's 0, so we have no EMF. There we have a maximum rate of change, therefore we have a maximum EMF. So you get this sort of lag, they're out of phase with each other by 90 degrees. So this has to be in line with the field when we're going to get maximum EMF, and so it's got to rotate 60 degrees from there right around a further 60 degrees. So that's got to come down that next 60 degrees there. So it's going to be 60 degrees. Then calculate the maximum angle and minimum angle in radians to which the coil must rotate before the flux linkage reaches maximum value. Well, it's going to go 60 degrees to there where there's no flux linkage, and then it's got to go around another 90 degrees to there where it'll be cutting the field lines perpendicularly, so we have maximum flux linkage. So it's actually got to be that 60 degrees first plus another 90, which is 150 degrees, sorry. Okay, it's 150 it says there. And then we have to convert 150 degrees to radians, so well, that's the fraction 150 out of 360 times by 2 pi. That gives you 2.6 radians. B shows how, figure 2 shows how starting at a different position, the flux linkage to the coil varies with time. What physical quantity is represented by the gradient of the graph shown in figure 2? Well, there it is, there's figure 2. The gradient of the graph is the rate of change of flux linkage, and the rate of change of flux linkage, because it's a graph of flux linkage versus time, so the gradient is the rate of change, and as you know, the rate of change of flux linkage by Faraday's law is the EMF, the voltage in the coil. So it's the EMF. Calculate the number of revolutions per minute made by the coil. Well, you can simply read this off the graph. The time period for one complete oscillation, one complete cycle, is 40 milliseconds. Okay, so it's 40 milliseconds, and therefore we think, well, that's our time for one oscillation or one cycle. There's 60 seconds in a minute, so I'm going to do 60 divided by 40 milliseconds, and that gives me 1,500. Alternatively, you could just say there, well, what F equals 1 over T, that's 25 hertz, and then 25 hertz times by 60 is 1,500. It's the same. Okay. Next point down here tells us to calculate the peak value of the EMF generated. Remember, the EMF in the coil is going to be the flux linkage times by the angular velocity, or 2 pi f. Okay, so we will put in there 0.55. That's simply reading off the graph. Okay, that is basically what the flux linkage is, times by 2 pi times by 25 hertz, which is the frequency which I just worked out up here. And that gives us 86 volts. So I omitted to put a very good scale on this, but that's 80, and I've tried to put that at just over 85. Okay, so I went up 20, 40, 60, 80, and just a bit more than that for 85. Okie dokie, so that's that one. Then it says, for question C, sketch the graph above to show how the EMF is induced over time. Now remember, here the gradient is 0, so here the EMF is 0. Here the gradient is a maximum, but it's a positive gradient, so this must be a minimum gradient down here. Okay, remember Faraday's law states that the EMF is basically, Faraday's law basically says E equals minus d phi over dt. And it's because it's opposed, it's to do with Lenz's law, isn't it? The fact it's opposing each other. So there you go, and that's maximum positive, that's minimum negative. And so you get this shape here. One mark, I think, is for getting these in the right place. The second mark, I think, would be for getting the fact that when this is a positive gradient up here, this is a negative value down there. And then it says, finally, D, the coil has a 550 turns and a cross-sectional area of 40 times 10 to the minus 3 meters squared. Calculate the flux density of the uniform magnetic field. Well, basically, the total flux linkage is BAN. And so you want to know what the actual field is. It's going to be the total flux linkage, which is 0.55, divided by the area times by the number of turns, and that gives us 0.25 Tesla.